Thank you very much. Good afternoon, ladies and gentlemen. My name is Art Benjamin, and I am a mathemagician. What that means is I combine my loves of math and magic to do something I call mathemagics. But before I get started with anything mathematical, I thought I'd begin with a magic trick. It has nothing to do with math, really. It's just a really cool trick. But for this, I'll need a volunteer to assist me. Someone here I do not know. I don't see any hands here. Let's see. And how about you, sir? What's your name? Ben. Let's give Ben a nice round of applause. Come up here, Ben. Ben, is that short for Benjamin? No, oh, it's not. It's just Ben. Okay, I'm Benjamin, and I'm a short Benjamin too, but that's another matter. Okay, anyway, Ben, have we ever met before? You seem proud of that fact, okay? Well, then I'm going to show you and everyone here a card trick that has never been seen before. Never been seen before because no one can see the cards. Ben, if you would, pick a card, any card at all from the deck, just one. Look at the card, show it to everyone, but do not let me see it. I will shuffle the rest of the cards so you see they're not in any particular order. Ben, I'd like you to place the card back inside the deck. But just to make it interesting, turn the card upside down first. Upside down, please. Good. Notice all the cards are face up except for Ben's, which is face down. Now watch carefully, as this took me years of practice. Watch, watch, watch. As I make the deck of cards disappear from my hands, reappear inside of this box, a box which only moments ago was empty. Trust me. Now I realize, Ben, what you were doing a moment ago was just a figment of your imagination, but what was the card, for that brief second at least, that you imagined that you selected? Ben, what card did you imagine? The Ace of Spades. Now, Ben, let me tell you, I know there are some people in the audience who are mumbling right now, oh, I'll bet everyone thinks of the Ace of Spades. Now, I'm not going to make you switch, but I'm going to give you this opportunity, because it is a somewhat commonly thought of card. You may change your mind or keep the mind you already have. The choice is yours. What would you like? You'll keep it. Well, I knew you would, Ben, because you'll notice in this deck that one card, and only one card, has been turned upside down. Would you be so kind as to show everyone the upside down card? Go ahead. The Ace of Spades. And let's give Ben a nice round of applause. Thank you very much. Thank you, Ben. Great. Well, while you're trying to figure that one out, I have another question for the audience, and maybe to get a little house lights for this. By any chance, did anyone happen to bring with them this afternoon a calculator? If you have a calculator with you in your wallet, in your purse, on your iPhone, and you're comfortable using that calculator, raise your hand. All right, I see one gentleman here, one, and let's see, okay, two, and all right, how about this gentleman, green shirt, t-shirt, three, and in the white shirt, yes, you waving your hand, four. Would the four of you please join me up on stage, and let's give these volunteers a nice round of applause. Come on up. Great. All right. One, two, three. One more round of applause for our brave volunteers. Come on up. Okay, over on this side. Now, since I have not had the chance to work with these calculators, I need to first make sure that they are all working properly. Would somebody get us started by giving us a two-digit number, please? How about 35? And another two-digit number, sir. 94. Multiply 35 times 94. Make sure you get 3,290, or the calculators are not working. Are all of your calculators working? 3,290. Give them a round of applause. Now, I notice that took some of you just a little bit of time to get your answer. That's okay. I'll give you a shortcut for multiplying even faster on the calculator. There's something called the square of a number, which most of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25. Right. Now, the way we can square on most calculators, let me demonstrate with yours, is by taking the numbers such as 5, pressing times, and then equals. And on most calculators, that will give you the square. Your calculator is sending me Wi-Fi messages, so I can't figure that out right now. But on some of those trickier calculators, they have an x squared button on it. We've already voted one person off the island. Terrific. We're down to 4. We'll see who the survivor is. All right, but you're all comfortable? You know how to square numbers on your calculator? Great. What I'm going to try and do now is to square in my head 4 two-digit numbers faster than they can do on their calculators, even using the shortcut method. What I'll ask is for 4 people in the second row here, how about 1, 2, 3, 4? Each of you yell out a 2-digit number, and if you would square the first number, the second, the third, and the fourth, I will try and race you to the answer. So quickly, a 2-digit number, please. 82, you said? Okay. Next. 73. Next. 37. Okay. One more. 46. Would you call out your answers, please? 6,724. 5,329. 1,369. Thank you very much. Let me try to take this one step further. I'm going to try to square some 3-digit numbers this time. I won't even write these down. I'll just call them out as they're called out to me. Anyone I point to, call out a 3-digit number. Anyone on our panel, verify the answer. If I get the answer right, give me a thumbs up. If I make a mistake, let me know, and I'll try and fix it. A 3-digit number, sir, yes, 3 digits. 176 is 30,976. 30976. Yes, good. Another 3-digit number. Sir, yes. 777 is 603,729. 603729. Good. Another 3-digit number, please. 315 is 99,225. 99225. Good. Another 3-digit number. Yes. 279 is 77,841. 77841. Yeah. Okay, another 3-digit number, sir. 931. Oh, that's a hard one. 931, is that 866,761? 866,761? Maybe not. What was it? What was the number? Was it 931? Let me try that one. 866,761. No, yes. Oh, okay. So it's like, another 3-digit number, please. 223 is 49,729. Thank you very much. Thank you. Let me try to take this one step further. I'm going to try to square a 4-digit number this time. Now, I'm not going to beat you to the answer on this one, but I will try to get the answer right. To make this a little bit more random, let's go to the second row this time here. If I can get the first 4 of you to call out a single digit between 0 and 9, that will be the 4-digit number that I'll square. 8, 7, 2, 5. 8725. This will take me a little bit of time, so bear with me. 8725. All right. 76 million. Is it 127,625? No, don't say it. 125,625. Thank you very much. Forgot to carry the 2, you know? Hate when that happens. I would attempt to square a 5-digit number, and I can, but unfortunately most calculators cannot. 8-digit capacity, don't you hate that? So since we've reached the limits of our calculators, I'd like to conclude the first, although your calculator, yeah. I'll talk to you later. In the meanwhile, since we've reached the limits of some of our calculators, I'd like to conclude the first part of my show by trying something a little trickier. Let's take, on your calculator, I want you to enter the year my first daughter was born, 1998. Would you each enter 1998 on your calculator? And instead of squaring it this time, I'd like you to take that number and multiply it by any 3-digit number that you'd like. But don't tell me what you're multiplying by, just multiply it by any random 3-digit number. So you should have as an answer either a 6-digit or possibly a 7-digit number. How many digits do you have in your answer? 6, 6, 7, 6. Is there any possible way that I could know what 6 or 7-digit numbers they have? Say no. Good. Then I shall attempt the impossible, or at least the improbable. What I'd like each of you to do is to call out for me any 5 of your 6 digits, or in your case, 6 of your 7 digits, in any order you'd like. 1 digit at a time, I shall try and determine the digit you've left out. So starting with your 6-digit number, call out any 5 of them, please.
5, 4, 4, 3, 7.
Did you leave out the number 5? Good, that's 1. You have a 6-digit number, call out any 5 of your 6, loud and clear.
7, 1,
Did you leave out the number 7? That's 2. You've got a 7-digit number, call out any 6 of yours in any order. I think you left out the number 4. That's 3. The odds of me getting all 4 of these right by pure guessing would be 1 in 10,000, 10 to the 4th power. Okay, any 5 of yours, really scramble them up this time. 1, 4, 3, 5, 8. Did you leave out the number 6? And let's give all 4 of these people a nice round of applause. Thank you very much. Thank you. Now, for my next number, I'd like to present something we mathematicians refer to as magic squares, kind of like Sudoku for magicians. Now, I have done such an extensive study on magic squares that I'd like to create one for all of you right before your very eyes. But for this, I'll need another assistant, someone here I do not know, and let's see, I do not know. You in the green shirt, what's your name? Let's give Maddie a nice round of applause. Come here, Maddie. Maddie, is that M-A-D-D-I-E? Good, I got it right. Okay. Maddie, if you would stand right there. Now, Maddie, I'm going to ask you another question, and if it's too personal, I can change the question. Maddie, are you willing to share with us your birthday, including the year?
Yeah.
Yes, great. Maddie, what is your birthday?
March
March 15th,
15th,
3/15, 1997. So that's your birthday, 3/15/97? Great. If we were to add the numbers in your birthday together, Maddie, we'd get 3 plus 15 is 18, plus 9 is 27, plus 7 is 34. So 34, Maddie, becomes your magic number. What I'm going to try and do now, Maddie, is to fill out the rest of this box in such a way as to get your magic number appearing here as much as I possibly can. This will take me a couple of seconds, so bear with me. I think that works. Maddie, would you choose for us any row? Row number 2, 3, or 4, which would you like? 3. Okay, class, together. 8 plus 10 is 18, plus 14 is 32, plus 2 is 34. The others were 3, 18, 27, 34, 8, 16, 18, 34, 15, 16, 25, 34. Would you choose a column, Maddie? 1, 2, 3, or 4? 3. Okay, class. 9 plus 2 is 11, plus 14 is 25, plus 9 is 34. The others were 3, 11, 19, 34, 15, 23, 33, 34, 7, 23, 25, 34. How about that? Now, Maddie, I'm not through with you. I decided that since this was your magic square based on your birthday, at no extra charge, I would give you these diagonals as well. Check it out here. 15 plus 10 is 25, plus 2 is 27, plus 7 is 34, 3, 11, 25, 34. But I didn't stop there either. I decided that since this was magic square was for Maddie, wouldn't it be great if we could get these 4 in the center to add up as well? Check it out here. 8 plus 2 is 10, plus 14 is 24, plus 10 is 34. But did I stop there? No, Maddie, you may have noticed I put a little extra attention in that corner. I did that so I could get these 4 squares. 3 plus 15 is 18, plus 8 is 26, plus 8 is 34 to add up. And I figured, heck, as long as we got that group of 4, let's have a party. We may as well get this group of 4, 9, 16, 32, 34, 8, 18, 19, 34, 14, 16, 25, 34. But did I stop there? No, I said Maddie wouldn't be happy unless we got this group of 4, 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 this group of 4. Now I have to, how I even was able to get this group of 4 and that group of 4, and I usually don't get that. But I had to do it that way, Maddie, because if you, here's the cool part. If you look at these 4 in the corners, 3, 10, 19, 34, not only do they add up to 34, but check this out. I was able to give you 3, 15, 97. I was able to give you your birthday a second time, which I thought you'd like. So keep this as a souvenir, and let's give Maddie a nice round of applause. Thank you, Maddie, very much. Thank you, Maddie. By any chance, does anyone here happen to know the day of the week that they were born on? If you think you know your actual birthday, raise your hand. All right, start with the gentleman in the green shirt. What year? 1978. And what month? February what? 28th. Was that a Tuesday? It was. Good. Somebody else. Yes. Okay. How about? Okay. Boy waving his hand. What year? 97. And the month? January what? 28th. Was that a Tuesday? Oh, looking uncertain there. I don't mean not this year, but the year you were born. Was that a Tuesday? I'll get back to you later on that. Somebody else who's really sure now. How about, okay, in the blue shirt, what year? 1997, okay, like your friend. And what month? April what? 10th. Was that a Thursday? Mommy is saying yes. I'm going to go with her. How about you? What year? 96. And the month? April what? 14th. Was that a Sunday? Good. And, okay, one more. And, okay, in the back. Yeah, go ahead. What year? 2001. Yes. And the month? November what? 13th. Was that a Tuesday? Thank you very much. Yes. Now, where was that Tuesday child that I was in a disagreement with? Who is it? Where is he? There you are. Okay, so I come prepared for these disagreements. I brought along with me a book of calendars. Goes as far back into the past as 1800, because you never know. I didn't mean to look at you, sir, when I said that. You were just sitting there. But if I can get one of you to help me out here just for a moment. So go ahead and give us your birth date again, and we will double check it on our calendar. So you said was it 97? Okay, so turn to the calendar with 1997 on it. And what was the birth date? January 28th, and I'm pretty sure that's a Tuesday. Let's double check that. It is Tuesday. Your mother lied to you. What can I say? She's going, oh no. I'll tell you what, as long as you have that book with you, do me a favor, turn to a year outside of the 1900s, either in the 1800s or way into the 2000s. That'll be a much greater challenge for me. What year, go ahead, what year would you like? 1874, okay. And what month? March what? 3rd. Was that a Tuesday? And it was cloudy, I think. Thank you very much. Thank you. Was it? Now, folks, if I were performing for a different sort of audience, like say at the Magic Castle in Hollywood or Disneyland, as I occasionally do, I would follow this up with other feats of magic and mind. But for an audience such as this one, especially here at the World Science Festival, I thought it would be better, more fun actually, to actually break the magician's rule and explain to you most of what you've seen me do up here and more. In fact, I'd like to conduct the rest of this program, the next 30 minutes or so, very informally. So feel free at any time to interrupt me with questions, even if it has nothing to do with what I'm talking about. It's much more interesting that way. But inevitably, the first question is, okay, start explaining. How do you multiply numbers so quickly? So let me start with that one, and then I'll take your questions about anything at all. We'll even have a couple of runners out here in the audience for people who have questions. They'll put a microphone in your face. Wave your hands if you're, okay, just so when you have questions, make sure they see you. Okay, so let me start with that question. How do you multiply quickly? And then I'll take your questions about anything at all. Now, I like to do everything by example, and I'm going to start you off with a 2-digit number times a 1-digit number, and then we'll work our way up to bigger problems. How about a 2-digit number times a 1-digit number as our first problem? 27 times 5 is 135, and here's how I do it. Now, if there's only one thing you remember from this entire presentation today, it should be this. I do all of my calculating from left to right. All right? Now, that's the opposite of how you might do it on paper. On paper, most people go from right to left, and that's fine for doing it on paper. But if you want to do the math in your head, like I do, then I say you should do it from left to right. Let's do it now. So 5 times 20 is, of course, 100. 5 times 7 is 35. Add those together from left to right. What's 100 plus 35? 135, and that's the answer. Now, this was made a little bit easier because of that 5 and that even number 2, because the 100 plus the 35, there was literally no adding that had to be done. 135 adds to 135. If the problem had been slightly different, if, say, the problem had been 27 times 6, then it would have been similar. 6 times 20 is 120. 6 times 7 is 42. Add those together from left to right. And though we have a little bit of addition, it's just 1-digit addition to get 162. Again, it took me about a minute to explain these problems, but trust me, with just a little bit of practice, you can do any of these problems in just a matter of seconds. It just takes a little bit of practice. But let me show you now a few things that you can learn to do right here, right now, that'll take you almost no practicing at all. Starting with one that's especially well suited for the very youngest members of our audience. So for those of you here, here's something that I think you'll enjoy. How to multiply in your head the number 11 times any 2-digit number. Very easy to do once you know the secret. Give us a small 2-digit number just to get started. 32. 32 times 11 is as easy to do as 3 plus 2. 3 plus 2 is 5, and there's your answer, 352. 352. All right? Here's another one. Let's say the problem had been, 53 times 11. 5 plus 3 is, so what's the answer? 583. You got it. Okay, one more. This time I want to hear everybody give me the entire answer, not just the middle number. As soon as I write it down, tell me 81 times 11. What is it? 891. Give yourselves a nice round of applause. I know. All right, you have a question. I bet I know what it is. What's your question? What do you do if the numbers add up to something bigger than 9? Suppose we had a problem like 85 times 11. 8 plus 5 is 13, but the answer is not 8, 13, 5, I'm afraid. We only have room for the 3. But the 1 makes the 8 carry, and the answer is 935. You got it. Here, let's try another one. Let's say the problem was 57 times 11. Now, 5 plus 7 is 12. So what's the answer? 627. You got it. Okay, one more. This time I want to hear everybody when I count to 3. So when I say 3, and not before, I want to hear everybody tell me 77 times 11. 1, 2, 3. 847. Give yourselves another nice round of applause. Good job. All right. Well, folks, I've got, hours and hours of stuff that I could talk to you about, and I'd love to share with you. But because I saw a bunch of hands go up just minutes ago, I think I'm going to spend most of the rest of the time answering your questions. So let me take those now, and we'll just see. I want to talk with whatever you are most interested in. So let's see, starting with, okay, I see a person in the black shirt right there. Yes, what's your question? And we even have someone who can give you a mic.
Do you have a website with your tips and tricks?
Do I have a website with my tricks and tips? I did not plant that person in the audience. Well, I'll tell you what. If you're interested, the easiest thing to remember, because websites are funny, just if you search on my name, Arthur Benjamin, then I'm happy to say that I'm the first name and website that shows up, so you can go on and check there. I do have some books on how to do math in your head. In fact, tomorrow there will be a book signing or you can get them online or at any bookstore, Secrets of Mental Math. Let me take this as an opportunity to say, when you go to my website, that you'll also find my college. And whenever I speak, my college really likes me to say this, so I will. I teach at a school called Harvey Mudd College. Yay, Harvey Mudd. It's a funny name, but if you say it fast, it sounds like Harvard Med. So it's even more impressive if you say it fast. It's a small school in Los Angeles area, 750 students, all of whom major in math, science, and engineering. And what I love about teaching there is the students are not only trained to be excellent mathematicians, scientists, and engineers, they're also taught so that they really have an understanding of the impact that their work will have on society. That is the mission of Harvey Mudd College. So for all of you bright young mathematicians and engineers out there, if you're thinking about going to a great school where you can study as much math and science as you want, please consider Harvey Mudd, and I'll be one of your math professors, which can be a good thing or a scary thing, depending on how fast you like your math. Okay. Other questions? Yes, sir. White T-shirt. The question was, did I memorize? I'll be honest with you. I do have memorized the squares of the 2-digit numbers, the numbers up to 99. I've been doing the squares of 2-digit numbers since I was like in 8th grade or so. So a lot of those have just unintentionally become memorized. But 3-digit numbers and beyond, except for a handful of 3-digit numbers that people yell out a lot, like 1, 2, 3, or 4, 5, 6, or 666 gets called out a lot. I don't know why. I have, except for a handful of them, I'm actually calculating them. Let me show you. Let me use this as an opportunity to explain to you the method that I use for squaring numbers, starting with 2-digit numbers, and then I'll show you how that continues on to do 3-digit numbers or higher. Somebody give us a small 2-digit number just as our first problem. 79 is not a small 2-digit number. So for our first problem, how about another 2-digit number? Okay, I'll go with 14. And Now, I have that one memorized. Maybe some of you do. Anyone know it off the top of their head? 196. Got a few other mathematicians in the audience. So let me show you how you could square 14 using my method. Now, 14 is not a bad number to multiply, but what number close to 14 is much easier? Well, I heard someone say 11 because I just taught you 11. Absolutely. But even easier than that is 10, right? So, because multiplying by 10 is just attaching a 0, and I like zeros a lot. So, I'm going to go down 4 to the number 10. And therefore, I go up 4 to the number 18. So whatever comes up must come down. I have to keep it balanced. If I go down 4 to 10, I have to go up 4 to 18. Now, 18 times 10 is what? 180, right. Almost done. All we have to add to this is the square of the number that we went up and down. We went up and down 4. 4 squared is 16, and there's your answer. 180 plus 16 is 196. Let's do a couple more because I want to make sure you get really good at these, okay? How about another two-digit number? Sure. 17, okay. So this time the nearest easy number would be 20. So let's go up 3 to 20. If I go up 3 to 20, I have to go down to what? 14. So next we do 20 times 14. Well, 2 times 14 is 28. So 20 times 14 is 280. Almost done. All we have to add to that is what? 3 squared, which is 9. So there's your answer, 289. Yeah, let's hear it for algebra. This is great. Tell you what, just in case, I heard somebody say, well, if you wanted to square the number 17, somebody said, well, I'd rather go down 7 to 10. Can I do that? Sure, of course. Go down 7 to 10 if you want. Now you go up 7 to what? 24. What's 24 times 10? 240. And what do we add to that? 49. 240 plus 49 is? It's still 289. Now, I don't know about you, but I think that's kind of cool. I mean, that you could take a problem, do it lots and lots of different ways, and if you're careful, you'll always come up with the right answer. I found that consistency of mathematics to be absolutely beautiful when I was a kid. I just loved doing that. In fact, I'm still in love with doing that today. I like taking problems, looking at them from different angles, and seeing what we can see when we look at things from different angles. Other questions? Yes, what's your question? Great question. So his question was, I see you can square numbers, maybe cube numbers. Can you go in reverse? Can you do square roots or cube roots? No. Or his question was something probably not as good for me, but go ahead. Well, say that again. A low number to a high power. I can cube numbers pretty quickly. That's not something that's a normal part of my show, so I'm not quite as at practice at it. But yes, question? An interrupting question. Yes, sir. I think he said low numbers to high powers, right? 6 to the... So the question is, I don't do numbers to like 6 to the 27th power. That's out of my range. But the last digit is 6, because 6 to any power, 6 times 6 ends in 6. And when you keep multiplying it by 6, it still ends in 6. So okay, I can give you one digit of the answer. Let me take another question. Yes, sir. Okay, so what if you want to square a number that's bigger than a 2-digit number? Go ahead, sir, give us a 3-digit number, and I'll show you what I do. Yes? So give me like a 3-digit number. Oh, a large two-digit number, like 79. Okay, so let's do 79 squared. So 79, the nearest easy number would be 80. So we go up 1 to 80. Therefore, we go down to what? 78. And now we do 80 times 78. Now that's 8 times 78 with a friendly 0. Let's try and do 8 times 78 together in chorus, okay? 8 times 70 is 560, 560. 8 times 8 is 64. Now left to right, 560 plus 64 is 624. With the 0, that's 6,240. And what do we add to that? 1, the square of 1. So quickly, before you forget it, 6,241. There you go. Okay? Now let me say that the process that I go through, you may wonder, is it visual or is it auditory? Am I seeing the numbers or am I hearing the numbers? For me, anyway, it's entirely auditory. I am hearing the numbers. I'm describing the process to you visually, but when I do 500 plus 300, I don't see the zeros. Rather, I know that 5 plus 3 is 8. So 500 plus 300 is 800. The word hundred lines things up, not in my eye, but in my ear. Okay? So anyway, so if you can do 79 squared, you could do any two-digit squared with just a little bit of practice. Yes, sir. What's your question? So he's saying, let's hear you do an even larger problem to understand the process that I go through. I will do that. Let me save that question towards the end of the show. I'll gladly show you that. But you know what? But I'll need a couple of things explained before then. Let me see where we are on time. Oh, we're almost near the end of the show. Let's see. Oh, and by the way, I'm just going to say this now, because if I don't, I'm going to forget later, because I see more hands than we have time. I will, after the show, be hanging out in the courtyard area, which is right that way. So when you exit, you can go back around, and I'll gladly answer questions individually for those that have them there. Okay, so just saying that now. Other questions? Yes, ma'am. How'd I do the card trick? Okay. If everybody asks me at the same time, how'd you do it? I did it very well. That's the only part of my show I won't explain. I would get kicked out of the Magicians Union if I taught you that trick. But anything else I'm willing to explain. Yes, please. Can I use math to solve the Rubik's Cube? Well, it just so happens that I have a Rubik's Cube here. In fact, here, I'll toss this to someone. Catch. Okay, take the cube, scramble it up. You can give it to one of your neighbors or friends. They can scramble it up. Now, you've probably seen people who are faster at solving the Rubik's Cube than I am, but I'm going to do something that you've probably never seen before. If you scrambled it to your heart's content, give it to your mother or somebody else, let them mix it up too. But I'm going to do something you probably haven't seen before. I'm going to try to solve this Rubik's Cube without even touching it. All right? I don't want to touch it. Okay, you've got it. Ladies and gentlemen, my daughter, Laurel. Laurel, come on out here. Laurel just recently learned to do the Rubik's Cube, and so I'm going to ask you not to hand it to me because I don't want to touch it, but please give it to Laurel. Okay, and now Laurel and I have a little contest going on. She's going to try to solve that Rubik's Cube in less time than it takes me to sing a song. I'm going to do a modern Major General from the Pirates of Penzance. Those of you that know it can sing along with the chorus with me, but only the chorus, please. And at the same time, I will simultaneously demonstrate to you that there's no connection between talent in math and talent in music, okay? So, Laurel, are you ready? Ready? Go. I am the very model of a modern major general. I've information, vegetable, animal, and mineral. I know the kings of England, and I quote the fights historical from Marathon to Waterloo in order categorical. I'm very well acquainted, too, with matters mathematical. I understand equations both the simple and quadratical. About binomial theorem, I'm teeming with a lot of news. With many cheerful facts about the square of the hypotenuse. And if you know the chorus, with many cheerful facts about the square of the hypotenuse. With many cheerful facts about the square of the hypotenuse. Many cheerful facts about the square of the hypotenuse. I'm very good at integral and differential calculus. I know the scientific names of beings and animalculus. In short, in matters vegetable, animal, and mineral, I am the very model of a modern major general. I know our mythic history, King Arthur and Sir Caradox. I answer hard acrostics. I have a pretty taste for paradox. I know, quote in elegiacs, all the crimes of Heliogabalus. In conics, I can floor peculiarities parabolus. I can tell undoubted Raphaels from Gerard Dowson's Zophanies. I know the croaking chorus of the frogs of Aristophanes, and I can hum a fugue of which I've heard the music's dinner and whistle all the airs from that infernal nonsense pinafore, and whistle all the airs from that infernal nonsense pinafore, whistle all the airs from that infernal nonsense pinafore, whistle all the airs from that infernal nonsense pinafore. She is the very model of a modern major general. Thank you, Laurel. All right. I should say that my wife is also has a mathematics background, and when we had kids, there was some concern that we might give our kids mathematical names. You know, like if it was a boy, Adam; if it was a girl, Subtractum. You know, but happily we did not. So. Anyway, I did not set up that question, but thank you for asking it. Yes, sir, question. How do I solve the calendar problems? Because we are close to the end of the hour, I'm going to not go into all the details, but I'll give you a little bit of the ideas. And it's mathematical. The calendar is itself a very mathematical object. It's based on the fact that what normally happens to your birthday as you go from one year to the next? What usually happens? It goes up a day. Why is that? It's because there usually are 365 days between your birthdays, and 364 happens to be a multiple of 7. It's 7 times 52. So if every year had 364 days, your birthday would be on the same day each year, and that would be boring, and that's why they don't do it that way. And something about the Earth and the Sun, right. So, but since it's 365 days, it usually bumps up by a day, except for those leap years where it bumps up an extra day after that. And based essentially on just that fact, you can figure out the day of the week of any date. Now, what I'll do is, you give me your birthday, if you're willing, and I will calculate the birth date. It won't make, I warn you, it will not make sense to you, but at least you'll hear what goes on in my head. So I asked for what year, first of all? 59. I take 59 plus a quarter, that is 73, and mod 7, I subtract 70 to give me 3, and then I say what month? July, and every month gets a code, and July's code is 0, and then I say July what? 14th, and that's a multiple of 7, so I'm still at 3, and the third day of the week is Tuesday, so you're born on a Tuesday. Thank you very much. I told you it wouldn't make sense. It's something it's explained in my book and on other websites, and it's something that with a little bit of practice anyone can do. Yes, sir. Question. How long have I been teaching? I've been at Harvey Mudd College now. I just finished my 20th year as a professor at Harvey Mudd College. Yay. Best job I've ever had, and only job I've ever had, really. As far as how I got started, it was really a combination of two loves. As a kid, I loved showing off. I grew out of that, of course, but I enjoyed magic and doing all kinds. You know, I did traditional magic shows for children when I was in high school. I would go to birthday parties and do the rabbit out of the hat kind of stuff. And independent of that, I had an interest in math. I've always liked playing with numbers, like what you're seeing here today. And eventually, about the time I started college, I combined my math talent and my magic talent and put together these math shows, and it just took off from there. So that's a short version of what I'm doing. Yes, question? For those problems up there? Yes, very good question. She said, for like a 3-digit number, would you go up or down to the nearest 100? And that's exactly what I do. Give us a 3-digit number, and I'll show you. 802. Okay, that's a nice one to illustrate. Here, of course, because 802, you're going to go down to what number? 800. So we go down 2 to 800. We're going to go up 2 to what? 804. And now 8 times 804, we can do that left to right, is what? 8 times 804 is 6,432. Don't be intimidated. It's just 8 times 800 is 6,400. 8 times 4 is 32. You get 6,432. Attach the 2 zeros this time, yeah? So here are 2 zeros. And so we have 600, so give me the answer. 643,204. Right, and there's your answers. Okay, thank you very much. Let me take, yes sir, what's your question? What are my research interests? As a mathematician, my favorite subject is something called combinatorics, which is basically the mathematics of counting things. I've always had a strong attachment to numbers. I don't do as much with things that are like as much in the way of geometry or differential equations or calculus. I use it in my work, but I've always had a real passion for numbers. And my favorite numbers out there are Fibonacci numbers. So Fibonacci numbers, even for those of you young ones out there, can understand them. Because they start with 1 and 1, and we all know 1 plus 1 is 2, and then 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, 13, 21, 34, and so on. These are the Fibonacci numbers. And you could spend your life looking for patterns, beautiful patterns that live inside of these Fibonacci numbers. For example, like if you like to square numbers like I do, we know that 3 squared is 9, and what do its neighbors multiply to? 2 times 5 is 10, and those are just 1 apart. How about 5 squared? 5 squared is what? 25. And what do its neighbors multiply? 3 times 8? 24. And those are just 1 apart. Here, let's do one more. If I square the number 8, that's equal to 64. And if you multiply its neighbors, 13 and 5, you get 65, which is just 1 apart. Okay, and suppose you took a number and you spread them out farther. Instead of looking to the neighbor, 1 to the left and 1 to the right, what if you went 2 to the left and 2 to the right? And you multiply those. You know what? They still are just 1 apart from the square. And if you go 3 in a row, 3 to the left and 3 to the right, you know what you get? It's not 1 apart anymore, it's 4 apart. And if you go 4 to the left and 4 to the right, it's not 4 apart anymore, it's 9 apart. And you know where those numbers are coming for? 1, 1, 4, 9, 25. They're the squares of the Fibonacci numbers. Anyway, I could go on and on and on about them, and don't let me do that. But that's the sort of stuff that I absolutely love. I'll tell you my other favorite number before I launch into my grand finale. My other favorite number is pi. Now what's pi, right? Pi, for many of us, pi is approximately 22 over 7. But that gives you like 3.142857. It's not a very, it's close, but if you want to get pi more accurately, it's, let's see, 3.1415. I know, how are you going to check it? Google, yeah. Here are the first 60 digits of pi. Thank you very much. Now, I can't help look at the number pi, and I just see it, and all I want to do is break into song. And so, if you'll indulge me one more time, something I wrote a few years ago in celebration of my favorite number, written to the tune that maybe not as many of the kids know in the audience, but I think some of the parents will appreciate. Once again, put up with my singing. Here we go. Long, long time ago, I can still remember how my math class used to make me snore. 'Cause every number we would meet would terminate or just repeat. But maybe there were numbers that did more. But then my teacher said, I dare ya to try to find the circle's area. Despite my every action, I couldn't find a fraction. I can't remember if I cried the more I tried or circumscribed, but something touched me deep inside the day I learned of pi. Oh, pi, pi, mathematical pi. Twice 11 over 7 is a mighty fine try. A good old fraction you may hope to supply, but the decimal expansion won't die. Pi, pi, mathematical pi, 3.14159265358 A good old fraction you may hope to define, but the decimal expansion won't die. Thank you. All right, one last thing for you, then I got to go. I want to respond to the question asked earlier about explaining my thought processes a little bit. So there was on stage at least one gentleman who had a 10-digit calculator with him. If you're still here, raise your hand, okay? Anyone else who has a big calculator, you're welcome to stay in your seats and pull it out and check it with me. What I'm going to try to do is square a 5-digit number this time, requiring a 10-digit calculator or higher. But to make my job more interesting for you as well as for me, I'm going to do this last problem thinking out loud. So you can actually, honestly, hear what's going on in my mind while I do a calculation of this side. Nothing to cry about. It's really going to work. I've done this many times, okay? I know. Let's create a 5-digit number. Let's go up the aisle this time. If I can get the first 5 of you to call out a single digit, that will be the 5-digit number that I square. Okay, starting with you. 6, he says. 8, 4, 7, 2. 68,472 squared. Yuck. Let me explain to you how I'm going to attempt this problem. I'm going to break the problem down into 3 parts. I'll do 68,000 squared plus 472 squared plus 68,000 times 472 times 2. Add all those numbers together and with any luck arrive at the answer. Now let me recap. Thank you. While I explain something else. As I do this calculation, you might hear certain words as opposed to numbers creep into the calculation. Let me explain what that is. This is a phonetic code, a mnemonic device that I use that allows me to convert numbers into words. I store them as words and later on retrieve them as numbers. I know it sounds complicated. It's not. I just don't want you to think you're seeing something out of Rain Man here. There's definitely a method to my madness. Definitely. Sorry. One last instruction for my judges with calculators. If you have a calculator, raise it so I just say, see it. Okay, a lot of you, good. there is at least a 50% chance that I will make a mistake here. If I do, don't tell me what the mistake is. Just say you're close or something, and I'll try and figure it out, which can be pretty entertaining in itself. If, however, I am right, whatever you do, don't keep it to yourselves. Make sure everybody knows that I got the answer right, because this is my big finish, okay? So, without any more stalling, here we go. I'll start the problem in the middle with 68 times 472. Now, 472 is 8 times 59. I'll take advantage of that. So we'll do 68 times 59 times 8. 59 times 68 is 3,400 plus 612 is 4,012. Multiply that by 8 to get 32,096. 32,096, double that to get 64,192. 64,192 becomes chair tippin'. Chair tippin' is 64,192. That seems right. I'll go on. Chair tippin'. Okay, next I do 68 squared, which is 4624. So I can say 4 billion. Take the 624, add that to chair. 624 plus the 64 is 688 million. Tippin', tippin'. Okay, next we do 472 squared. That's 500 times 444 plus 28 squared. It's 222,784. Cover if I need a cover. Take the 222, add that to tippin' to get 414,784. Yes, good. Thank you very much. I hope you enjoyed Mathematics. Thank you. Thank you.